We're really excited to kick off this next session with François Chollet, who's come in from San Francisco, where he's a software engineer at Google. He's well known for being the author and main contributor behind Keras. He's a prolific contributor behind TensorFlow as well. And he's going to come talk to us around deep learning and hopefully what comes afterwards. So with that, François, up to you.
Thank you for the nice introduction. So it's a pleasure to be here. My talk is about the limitations of deep learning and about how the field of AI is going to have to evolve to overcome these limitations in the future. So we've had a lot of great successes with deep learning lately. But the rise of deep learning is still a very new trend. Just 5 or 6 years ago, very few people believed in deep learning, believed in its potential. And now we've used deep learning to achieve remarkable results on a number of historically very difficult problems in machine perception and natural language processing. However, at the same time, it seems to me that most of the progress we've made actually happened between 2012 and 2016. And it might be that deep learning research is starting to plateau lately, at least in my perception, even though there are so many more people doing deep learning research today than 2 or 3 years ago. So the goal of my talk is to try to zoom out a little bit, to look at what deep learning really does, to look at what its limits are, and to try to see what the road ahead for AI might be. So if we're going to be talking about the limits of deep learning, of course, we need to understand what deep learning really does. So what's deep learning? First of all, it's not this. There's a lot of hype around deep learning, which serves in part to hide its true nature. This hype gives deep learning an aura of mysticism, especially when people, especially in the media, compare it to what the brain does. In fact, deep learning has very little to do with the human mind. So deep learning is more like this. It's a parametric model that fits some data. It's a differentiable parametric model that is trained with gradient descent. And to me, that's actually the most interesting and the most surprising thing about deep learning, is that it is, in fact, extremely simple. If you look back, like 10 years ago, no one would have believed that you could achieve the sort of results that we're getting today in machine perception using these very, very simple parametric models trained with gradient descent. It turns out the only thing you need is sufficiently large models, sufficiently deep models trained on sufficiently many examples. And this very simple idea can achieve extremely interesting results when you scale it. So that's, to me, that's the key surprise about our recent progress with deep learning. So in deep learning, everything is a vector. So everything is a point in some vector space. So you start with some data, which could be images, which could be videos, sound, language, text. And you start by vectorizing it. Essentially, you encode it in this very high-dimensional input vector space. And this input space is going to be mapped to a target space, which could be labels for images, for instance. It could also be other images if you're doing something like super resolution, for instance. And this point-by-point mapping is happening through a chain of layers. So what are layers? Each layer is basically a very simple geometric morphing between one space and another, between the input space of the layer and the output space of the layer, right? And it's a very simple transformation. It tends to be an affine transformation followed by a hard-coded squashing function like ReLU, or some variation of it. For instance, a convolutional layer is going to be an affine transform applied convolutionally. A RNN layer is a combination of affine transforms applied inside a for loop, and so on. And so that may seem a bit abstract, but you can actually visualize this process in 3D by trying to imagine someone trying to uncrumple a paper ball, a crumpled paper ball. So that paper ball is your manifold of input data, right? Like, for instance, say that you have 2 sheets of paper, you superpose them, and you crumple them together. And each sheet of paper was a class in some classification problem. And now you're trying to make them linearly separable again. And what you're going to be doing is applying a series of very simple gestures on the paper ball. And each atomic gesture is in a way comparable to the geometric operations implemented by one layer. It's in first approximation, you could say its gesture is an affine transform on the paper ball. And although each transformation is very simple, the total sequence of gestures implements a very complex geometric morphing that gets you to this flat sheet of paper again. So basically that gets you to linear separability of your classes again. So you could say that deep learning models are mathematical machines for uncrumpling very complicated manifolds of high-dimensional data. So it's really that simple. And one very important constraint that we have to keep in mind is that these chains of geometric transformations that we are training, they need to be differentiable, which is a requirement for us to learn their parameters using gradient descent. So intuitively, what that means is that the geometric morphing from input to output is going to have to be smooth and continuous. But because this geometric process of point-by-point input to output mapping does not model the human mind, deep learning turns out to be pretty bad at a lot of the things that humans are really good at. So in the previous talk, you learned about adversarial examples. In general, deep learning models are extremely sensitive to any sort of change in their input space, which totally makes sense if you think about what they're doing. If you're feeding this geometric morphing from input space to output space on some data, and then you're slightly changing the input manifold, like you're slightly changing the shape of the crumpled paper ball, then the sequence of gestures that you learned previously suddenly is mismatched with your new data, right? So that's why deep learning models are extremely brittle. Deep learning models can only make sense of what they've seen before, right? So effectively, they are a kind of template matching algorithm. And again, because they're learning this point-by-point input to output mapping between two spaces. And one very real risk with deep learning models is to misinterpret what they're doing and to overestimate their abilities. As humans, we have this tendency to project beliefs and intentions, like mental models, on the things around us. All right, that's our theory of mind. And applied to deep learning, that means that when we're able to somewhat successfully train a deep learning model to handle a task that would normally be performed by a human, then we are led to believe that the deep learning model understands what it's doing, that the process going on inside the model is somehow similar to the process going on in our own minds when we handle the same problem. But in fact, deep learning models are solving a very, very different problem, and they are doing so with a very different knowledge from the knowledge that you have. And that's why if you change anything, if you show a deep learning model anything that has not been trained on, right, it might break down in completely absurd ways, like in these pictures, in these mislabeled pictures. So our own understanding of images and language comes from our experience as humans. It is grounded in our experience, but deep learning models have no access to this experience. So they do not really understand their task in any human relatable way. The only thing they understand is, again, this mapping between their trained data to their target data. So if there's one thing you need to remember about deep learning is that it is pattern recognition. So essentially, it is a form of template matching that can only make sense of samples that it has seen before, that are very close to what it has seen before. So to be clear, it is very good at pattern recognition. And I'm not in any way trying to downplay the significance of being good at pattern recognition. This is actually immensely useful. Deep learning is applicable to a tremendous scope of very difficult and important problems in machine perception, because they are pattern recognition problems at heart. But importantly, deep learning is not the road to artificial general intelligence, right? Scaling up deep learning by adding more layers, adding architecture search, using these deeper models or training on more data is not going to get you to AGI. So in order to lift these limitations, to go beyond deep learning, we need some fresh ideas. So that brings us to the fundamental difference between what deep learning does and what the human mind does, is that deep learning models can only make sense of data points that are very close to what the model has seen before, to what it has experienced before. Meanwhile, humans are capable of covering vastly more ground using the same experience, or using relatively little experience. That is what I would call extreme generalization, as opposed to the sort of local generalization performed by deep learning models. And extreme generalization can only be achieved with abstraction and reasoning. So here's one simple cartoon-like example to try to understand this distinction. Let's say that you have a robot, and you're trying to teach it to navigate an urban environment while avoiding getting hit by cars. So if you're doing that with a deep learning model, then because a deep learning model, again, is this point-by-point input to output geometric morphing, right, between, in this case, between the sensory motor space of the robot and outcomes, like dying or not dying. Then in order to train your deep learning model, you would need to essentially expose it to every possible situation in your urban environment. And for each situation, you would need to give it a feedback signal about, is it going to die or not? And that would involve, dying millions of times. So it's not very efficient, right? And of course, if you transport your model, your robot, to a different city, like a strange city where people drive on the left, for instance, suddenly your model will break down in fairly absurd ways. It will have to relearn most of what it has learned before. It is extremely sensitive to any changes in its input data, again, because it has no access to things like abstraction and reasoning. On the other hand, humans, the average human being is capable of learning exactly this without getting hit by a car even once, which is truly remarkable if you think about it. Unlike deep learning models, which can only learn from direct experience, humans can learn things without having any experience of it, like through language, for instance, through abstract models, right? So, and that is enabled by abstraction and reasoning. So what does it take to achieve extreme generalization? Just by adding more layers and training on more data, we are not going to get deep learning to the same level of generality as the human mind. So we need some fresh ideas. I think it's going to take three things. We need better metrics, we need richer models, and we need stronger priors. So let's take a look. First of all, we're going to need better metrics. I strongly believe that you cannot make any progress towards a goal if you have no way to measure your progress. And looking at the existing benchmarks and data sets that people are focusing on in the machine learning community today, none of them seems to be really focused on measuring generalization capabilities or on measuring abstraction capabilities. We have no way to quantify generalization or to quantify abstraction, for instance. So I think there is a need for an ambitious new benchmark that will be focused on measuring precisely generalization capabilities, right? Generalization strength, and not just skill at a specific task given sufficient training data, which is not very interesting, in my opinion. So you could think of it as a sort of IQ test that would be applicable to machine learning algorithms, but also to humans, ideally, so that we could compare the capabilities of our creations with the capabilities of humans. You could call it a GQ test, a generalization quotient. And second, we're going to need richer models. If you look at existing systems that are capable of abstraction and reasoning, besides humans, they tend to be computer programs that are hard-coded by human engineers. So essentially, this is a case of human engineers taking their own mental models and encoding them in the computing substrate. And these models, obviously, are far richer than the sort of input to output matching realized by deep learning models. I'm talking about all the tool set that used to be known as symbolic AI, back when people didn't associate AI primarily with machine learning. Things like search, for instance, or formal logic, and so on. So I believe that in the future, we're going to have machine learning models that look much more like computer programs, like the sort of programs that you might be familiar with, than they do to just this sort of like paper ball uncrumpling business of deep learning. So the thing with deep learning is useful because it enables you to build programs that you could not otherwise develop by hand. Like, for instance, you could not task a software engineer with developing an image classifier by hand, right? You need to learn it, right? And deep learning does an extremely good job at that. But the thing is, the assumptions made by deep learning models, things that it needs to be essentially a smooth, continuous geometric morphing from one space to another, which implies you're going to need a dense sampling of problem space, which implies, also the fact that it needs to be differentiable in order to train and so on. These are extremely strong assumptions that are limiting the space of programs that you can use deep learning for, right? So that the ideas behind deep learning are just way too restricted, especially if you compare them to software that has access to variables, for instance, that has access to an external memory, that has access to classes and functions, that has access to databases, that has access to networking protocols, and so on, all the tool sets that any human engineer would be leveraging in their own programs. So I believe we are going to need to expand the hypothesis space of machine learning models. Machine learning models will increasingly start looking like computer programs today, like programs that can manipulate abstract models of the tasks that they're working on, instead of just operating this point-by-point input to output mapping between two spaces. So that doesn't mean, of course, that we're going to throw away deep learning. Why would we? Deep learning is tremendously useful. It is very, very good at pattern recognition, right, which is applicable to a wide range of problems. So I believe instead you will see future AI systems that blend together deep learning, that blend together geometric intelligence with symbolic intelligence. And these two are very complementary, right? Geometric intelligence, like deep learning models, provides the capability for pattern recognition and intuition, while symbolic AI provides capability for reasoning and planning and abstraction. So they are very, very complementary to build strong abstraction machines. So a few early examples of this trend are, for instance, AlphaGo from DeepMind, which blends together Monte Carlo tree search, which is definitely a tool from the symbolic AI tool search, with ConvNets, so a deep learning module that is being used to evaluate a board position in the game of Go, and also to predict what the best possible move is going to be. Another example is self-driving cars. So in self-driving cars, you're typically going to be manipulating an explicit abstract model of the world. So in this case, a literal 3D model, right? And you are interfacing it with the real world through deep learning models that can handle perception, that process the sensory motor space of your car in a way, right? And we need to keep in mind, of course, that these existing systems that blend together symbolic AI and geometric AI, like deep learning, currently they are hard-coded by human engineers. And the only parts that are learned are submodules that essentially handle intuition in the case of AlphaGo, or perception in the case of self-driving cars. But in the future, such systems will be generated end-to-end from data and from experiments. So here's how it would work. You would have this sort of program synthesis engine that would have access to a large library of primitives, of subprograms. And some of these programs will be algorithmic in nature, like tree search, for instance, like Monte Carlo tree search. And some of them would be geometric in nature. That could be deep learning models, for instance, or any other kind of parametric differentiable model. Some of them might even be pre-trained representations, geometric representations. And these geometric models provide capabilities for intuition and pattern recognition and perception. And the algorithmic modules provide these higher level world modeling capabilities, right? Reasoning, long-term planning, and so on. And all of this should be generated from data. So that's the field of program synthesis, right? Program synthesis, which so far has really been focusing on more like classical computer programming, but in the future will be handling this sort of hybrid geometric and symbolic models. So if you follow this vision and models, machine learning models get more complex, they get more program-like, and they're built on top of these very rich algorithmic primitives, then that means we're going to need more sharing and more reusing of knowledge across different problems, right? Because a lot of data sets simply do not contain enough information to train a model from scratch, right? So we're going to need systems that can do lifelong learning. And one way to put it is that we're going to need stronger priors, right? One way to think about it is that you're not going to learn English from scratch every time you open a new book, right? Instead, you open every new book with your entire knowledge of the English language that comes from everything you've read before, everything you've heard before. In fact, it's not just your knowledge of language that you're reusing. You are reusing your entire abstract world model when you try to understand a book. You approach every new task, every new problem with the entirety of your knowledge so far. And I believe machine learning systems in the future will behave exactly in this way. They will be doing lifelong learning. We'll be reusing algorithmic primitives and geometric primitives across different tasks. So I believe the long-term vision for the future of AI and deep learning is a process for generating models, for learning models from data that will closely resemble the workflow of software engineers today when they are developing new programs. So I think if you want to know how AI will operate in the future, you should look at how human software engineers are operating today. Machine learning is definitely going to be evolving in the direction of program synthesis, right? And ways that will handle program synthesis in the future will be very similar to current software development workflows. So if you consider the workflow of an engineer today, whenever you're solving a specific subtask, like parsing a JSON file, for instance, what you're going to do is that you're going to maybe learn on a specific example on a small set of JSON files, right? But then you're going to package your solution as an abstract and reusable library for parsing JSON, even though you've only had access to a few JSON files so far, but that was enough to infer the rules. And then you're going to put this reusable library online for other people to download and use, right? Engineers are constantly manipulating abstract programs that were developed on a different task than what they're currently doing. And that sort of abstraction is the holy grail of AI, right? So AI is going to be evolving along these lines, essentially along the lines of creating new programs by reusing primitives from this global library of algorithmic geometric subroutines. And so you would have essentially a sort of a meta-learning system, right? And anytime this meta-learning system would find itself re-implementing the same sort of program subroutine onto different but related tasks, then it would package it as a reusable abstract program, and it would upload it for later reuse. So that implements not only lifelong learning, but also distributed lifelong learning, because every AI system will have access to the knowledge of every other AI system, right? So essentially, you would have this process where, given a new task, you would be able to quickly assemble a program to solve this problem. That program will be leveraging modules from a global library that is perpetually updated with new reusable abstract routines, kind of like you can think of it as a GitHub in a way, but for AI. Some of these primitives will be geometric primitives that could be pre-trained representations, that could be architectures where you're going to learn the parameters, like a ConvNet, for instance. And some of these primitives will be symbolic, like research and so on, or control flow or whatever. And so this is actually very similar to software development today, right? And this whole process, because it will be capable of essentially handling any task, right? It would implement a form of artificial general intelligence. So remember what we're going to need. First of all, we're going to need better metrics. You cannot make progress towards something if you have no way to measure progress. Second, we're going to need richer models. So models that look way more like the sort of computer programs that you're familiar with than they do to paperable uncrumpling. And lastly, you're going to need strong priors. So you're going to need lifelong learning and distributed learning. Thank you. Yes, so we have time for a couple of questions. Yes?
Hey, Damon from ARM here. Do you think this need to revisit older ideas and classical ideas will accelerate or slow down the rate of progress, given how easy it is to adopt deep learning?
Right, so I think there's a lot of inspiration we can draw from past ideas, things like genetic algorithms, reservoir computing, and all the ideas from the space of symbolic AI. I feel like deep learning research has been too quick to discard some of these prior results. Of course, they need to be improved on, but I believe with the recent progress we made with understanding the significance of deep learning, we are in a much better position to leverage these old ideas, and it's definitely a good time to revisit them.
Hi. You talk about the importance of the intersection between traditional machine learning and symbolic AI. So will there be symbolic AI modules coming to TensorFlow? Or can you recommend any other useful toolkits?
So symbolic AI is today you would refer it simply as programming, as software development, right? TensorFlow is definitely about differentiable models, first and foremost. But of course, if you insert a TensorFlow model inside a Python program, then you are definitely building a kind of hybrid symbolic and geometric model, right? What's going to be interesting is to start generating such programs automatically. So essentially, program synthesis, right? And I do not know of any good framework, sufficiently general framework for program synthesis today. I think that's going to be the next wave of tooling in AI, and it's probably at least 5 years out.
It's actually, so you're talking from the side so far, only from the side of the code, which is amazingly interesting as well. But what about the side of the data? And so far, let's say it is a consensus to feed in data randomly, let's say, right? So it's a kind of randomized learning, if you will. Whereas if we talk about AGI, people actively learn and they try to learn something they're interested in and they find useful, right? So, and that's a little bit of a upper hand in this case, right? Can you comment on this, please?
Right, so I think there are two components to this. So one is curriculum learning. In most cases, when you're going to have a lifelong learning system, the way it works is that you are developing solutions for new problems by reusing some modules that were trained on prior problems. So of course, there is going to be a sort of optimal ordering for the sequence of problems, where some of the earlier problems will be reused in the later problems, kind of like levels in a video game in a way. On one level, that's very simple. You learn one specific skill, then you reuse it in the next level and so on, and it accumulates, so you can handle more and more complex levels. So curriculum learning is one thing. We'll need ways to automatically craft curriculums for training our machines, not just randomly sampling data,